Okay, okay.
Thank you. So today I'm going to be talking about one, our research about how we were able to solve the Rubik's Cube with artificial intelligence, the Rubik's Cube among other puzzles as well, and then some preliminary work involving explainability. So we can use AI to solve some of these puzzles, but how can we use AI to help somebody learn how to solve the puzzle if they didn't know how to learn? Furthermore, how can somebody collaborate with AI and give their own ideas about how to solve the puzzle to come up with some personalized solutions? Oh, okay, so first I'll give a little bit of motivation why AI and the Rubik's Cube are an interesting problem. And then we're going to talk about the algorithm we came up with called DeepCube. And at the center of it was value iteration and a search method. And so first I'll talk about what value iteration is, how we are going to use some approximation. And so we'll talk about some machine learning models and we end up using neural networks and why we make that choice. And then I'll talk about how we use search to help solve the Rubik's Cube. And then I'll talk about how we can use explainable artificial intelligence to allow people to collaborate with AI to find personalized solutions to the Rubik's Cube. So one of the reasons the Rubik's Cube is interesting domain for AI is because it has such a large number of combinations. I'm sure you all know it has 4 times 10 to the 19 possible combinations. So in order for somebody to solve this puzzle with a machine, you have to have a an intelligent approach. You can't just brute force your solution. You have to have an approach that prioritizes um, certain paths while deprioritizing other paths because you just won't have the time or memory to search every single combination. Also, um, solving these puzzles in a domain independent way. So without telling the machine certain domain dependent um, aspects about the Rubik's Cube that involve, say, for example, symmetry or group theory, has not yet been done in the field of machine learning. Also, this can be a very informative test bed. I'm sure you all know there are these shortest path solvers that exist for the Rubik's Cube that use a lot of group theory and mathematics to find actual shortest to solve cubes in the fewest number of moves. So we can actually compare to these and see how well AI is able to do this with um, only giving it the basic information about how the cube moves. And then also this is rooted in mathematics, group theory, and so we can look at the relationship between AI and mathematics using the Rubik's Cube. And then furthermore, Rubik's Cube is just one example of a pathfinding problem. So pathfinding problems require one to find a sequence of actions that converts one state into another. And so these are found in robotics, mathematics, natural sciences. For example, here we have a theorem proving, and we are trying to find a path from a set of axioms to the theorem that we'd want to prove. And then we also have chemical synthesis, which is similar, where you have some building blocks and you want to find a path between these building blocks and some molecule you want to synthesize. Similarly, you can do program synthesis and tasks in robotics as pathfinding problems. So solutions to the Rubik's Cube also are informative for solving these other problems as well. Now, in this work, we investigate 4 different types of puzzles. And so this is the Rubik's Cube, sliding tile puzzle, lights out, and soccer band. And so for people who aren't familiar, the sliding tile puzzle allows you to swap this blank space with any of the tiles horizontal or vertically adjacent to this blank space. And the goal is to get all the tiles in order. For lights out, you can press any one of these squares and it turns it on or off, as well as all of the squares that are directly horizontally or vertically adjacent to it. And the goal is to turn all the lights out. And then with soccer band, the goal is to use this green agent to move these boxes onto these red targets. And so we investigated 4 different types of these sliding tile puzzles. And these are just puzzles of different sizes. And so the largest one we saw was the 48 puzzle. And so this has 10 to the 62 possible combinations. So just a very large number of possibilities for this 48 puzzle. So is everyone here familiar with the concept of God's number and God's algorithm for the Rubik's Cube? Anybody? Okay, so these are just colloquial ways to refer to what's usually referred to, say, as the diameter of the Rubik's Cube. So that's saying if you could solve every state with the fewest number of moves possible, what is the maximum number of moves that you would possibly need? And so this is called God's number. And then God's algorithm is the algorithm one would use if you wanted to solve the Rubik's Cube in the fewest number of moves possible. So we can actually use this one algorithm called value iteration to figure out what God's number is and figure out what God's algorithm is. And so value iteration starts with a table that contains all of the possible configurations for the Rubik's Cube and maps the table to some value, which is the estimate of the cost to go. And the cost to go is just the minimum number of steps. The true cost to go would be the minimum number of steps that you would need to solve the Rubik's Cube. And so since you don't know it initially, you can just initialize everything to 0. Then what you can do is you can look at every state and you can update its estimate of its cost to go by looking at all of the possible actions you can take and the neighboring states that result from them. And you then update the cost based on the cost it took to transition to those neighboring states, plus this cost to go. So this is what the equation would look like in the context of the Rubik's Cube, where you're looking at every action and you're saying, what's the cost it would take for me to take this action in this, here we have state or configuration of the Rubik's Cube, and transition to this new state. So this is just a function that returns the state that happens when you take this action. So actions are just turning faces of the Rubik's Cube. And then you say, what's the cost to go of this resulting state? And this is, I forget what I wanted to say about the cost of every action in this case is just 1. So since we want to minimize this cost, this is the same as saying we want to solve the Rubik's Cube in the fewest number of moves. And so once we apply this value iteration enough times, we'll actually reach this convergence where this cost to go for all states doesn't change And when we reach this, what people call a fixed point, when we reach this fixed point, it will be guaranteed that we will actually have converged to the true cost to go. And so we can find God's number just by saying, what's the maximum number in this table? And then we can find God's algorithm by just using this cost to go function. And what we would do is we would turn the cube in a way such that we are minimizing the cost to go at every step. And so using this value iteration, we could find God's number and God's algorithm, which is a big problem in the Rubik's Cube community. And I'm sure you all know this has been solved, what God's number actually is, by Thomas Rokicki. And it wasn't using this algorithm because the state space is so large. So while in theory, this is a nice algorithm and it has these nice theoretical guarantees, you won't be able to apply this to the Rubik's Cube because the state space is simply too large. And so what Thomas Rokicki did is he used a method called iterative deepening A-star search. We're not going to go into it here, but he built a heuristic to tell how close you were to the solution, and he used a lot of information about group theory and the mathematics surrounding the Rubik's Cube to do it. So here's a visualization of what value iteration looks like. And so imagine you're this tractor here, and you want to get to this shuttle. And you can move up, down, left, or right. And so you're in this 10 by 10 grid, and there are going to be 100 states. So this is a lot easier to deal with, and we can use value iteration in this context because there are only 100 states. Now you'll see that this value iteration is propagating outwards from the goal. So once we reach the goal, we have a cost to go of course, 0, but we are initializing the cost to go of all these other states as 0. And note that in this environment, you have a high cost for, say, running over a plant or running over a rock, because that's undesirable. So if we look at this value iteration running, you can see how it's propagating outwards from the goal. And at every step, we're able to find the better action from the states, one more step away and one more step away, so on and so forth. And then this has pretty much converged except for these two states here on the left because they're just surrounded by these planets. So you have a very high cost associated with these states. So this is a visualization of value iteration. And so now after value iteration has reached this fixed point, we see that we can essentially get God's algorithm for this domain by just behaving greedily with respect to the value, the cost to go. So at every state, we're going to look at what's the cost of all my neighboring states, and I'm going to take the step that minimizes this cost. And in this situation, you have the actually negative cost of reward, but it's actually the same thing, we just flip the negative sign. And so these arrows point to what we would do if we want to minimize this cost at every state, and this would lead us to find a minimum cost path for every single state. So we can get God's algorithm just by behaving greedily with respect to this. However, like I was saying, the state space is simply too large. You're not going to be able to fit all of this in memory and have the time to iterate over 10 to the 19 configurations until you converge. So we're going to need some approximation. So we're going to need some architecture that takes as input a state, a configuration of the Rubik's Cube, and outputs its estimate of its cost to go. And this architecture should have far fewer parameters associated with it than there are states in the state space. So previously, the architecture for value iteration was a table, and this is just too much memory. So we need something that uses far fewer parameters than there are configurations. All right, so first we need to think about how we would represent the Rubik's Cube to a machine. So does anybody have any ideas of how one would represent the Rubik's Cube to a machine? So I have some configuration, I've scrambled the cube up some way, and then how would I tell the machine that this is what my Rubik's Cube looks like? Set of 6 matrices, okay. And what are the values in each of the entries? Okay. So for the matrices, what are the values in each of the entries? Alphabetical codes for the positions, okay. Now we need to represent this as as numbers. So how would we convert this to numbers? Okay, so each matrix would have a number, probably 1 through 6 for each one of the colors. Okay. Okay. So let's talk about this associating a color with a number. So one can say white is 1, yellow is 2, green is 3, so on and so forth. Now, the issue with this approach is that as you're representing this to a machine, you're implicitly saying for example, yellow is 2 times white. Since white is 1, yellow is 2, you're actually implying that there's a numerical relationship between yellow and white when there's not. So these are actually just different categories, but white is not half of yellow. Green is not 3 times white. So you're actually enforcing this relationship, and we need to be able to say there isn't a numerical relationship between these colors. They're actually just separate categories. And so one way you would do this is with a one-hot representation. And so every sticker is going to be associated with a vector of 6 numbers, where only one of them is 1 and the rest are 0. And so, for example, white can be 1 followed by 5 zeros, yellow can be 0, 1 followed by 4 zeros, so on and so forth. And this means that you actually are denoting that these are separate categories and not that there's a numerical relationship between them. So you have 54 stickers, and each one of them is associated with a vector of length 6. And so you have a representation size that's 54 times 6. So maybe there's some other ways to do it as well, but this is the way we went with in our work. Okay, so after actually related to the approximation architecture, related to how we're representing this is what architecture we're going to use. So we're going to assume that the relationship between any given configuration and the true cost to go is probably nonlinear and appreciably complex. Maybe it would be really hard to write this down by hand, based on some configuration, here's its true cost to go. So one of the simplest machine learning models we can use is a linear model. And so a linear model, of course, it's in the name, they're able to capture linear relationships in the data. And so on the bottom right here, we see a series of points, and we want to find a line that's going to capture this trend. So we have this input X and this output Y. We want to find a line that captures this trend. And we can do this with linear models that actually learn how to capture this trend. Similarly, here we have 2 classes, say red and blue, and we want to find a line that separates the 2. And so with linear models, we can do this as well. However, since we said that this relationship is probably nonlinear, linear models won't be able to capture this. So say, for example, you have this oscillating relationship, and then here it's called a two moons data set. And you won't be able to find a line that's going to be able to do this problem satisfactorily. So another model you can use is decision trees. And decision trees ask a series of questions and then come to a decision. And so you can try to use a decision tree to solve this problem. And one of the benefits is it's interpretable. You generally know how it's coming to a decision. However, they usually require that data be high level. So for example, if you just tell it where all the stickers are, this would be a lot harder than if you are telling it some very domain-specific information. So decision trees in this work we didn't use. Now what we ended up using were neural networks. And neural networks are inspired by the brain, and they are made up of some connections. And when these connections are strong, so every neuron is associated with some incoming connections and some outgoing connections. And when the activity of a certain neuron reaches a certain threshold, then these neurons fire. And so when these connections are stronger, this is going to cause this neuron to be activated more often, and when they're weaker, then it's going to cause them to be activated less often. And the when a neuron fires, it's sending a signal from itself to all of its outgoing connections. So neural networks can be trained, and when I say trained, it means that these weights can be adjusted so that we can actually try to minimize some error. And so say, for example, there would be some error between the updated cost to go and our current prediction of the cost to go. And we want to minimize this error. And so we can adjust these weights so that we can try to minimize this error. And the method people use to do this is called gradient descent. So generally, neural networks are trained via gradient descent. That's not the only way to train them, but that's usually the most effective. So here's a very simple example where we have a neural network with just one weight. So this is actually just a linear model. And we have one single input and one single output. And so here again, you see this relationship between X and Y, and we want to be able to minimize the error between what our neural network says and what the data says. And here we'll see our error function. And so this is just going to be the squared error. And we want to find this minimum point here. So we want our weight to be 0, actually, where the error is minimized. And not necessarily 0, actually. In this case, it's not 0, but this should be shifted a bit. But essentially, at this point, the error is minimized. And the way gradient descent works roughly is, say our error is somewhere over here, and we want to minimize it. We are going to look at the gradient, and we see that this has a negative slope. So this gradient here is negative, and therefore we're going to move into the positive direction to try to get to this minimum point. Now here, this is a nice convex function, but as this gets higher dimensional neural networks, the actual loss landscape gets to be very, very complex. So if we see gradient descent in practice, you'll see as this error starts to decrease, this line starts to fit the data better. So here's just a visualization of that working. All right. Now neural networks, they can be used to capture linear relationships if needed. If you know your data is linear, it's usually better to use a linear model and not a neural network. But the important thing is they can capture complicated nonlinear relationships. So you see here this 2 moons data set. This is the neural network learning the difference between these two classes. And then by fitting this oscillating function, the neural network also learns to fit this oscillating function as well. And so neural networks led to early success in things like digit recognition. So machines being able to recognize digits and things like that. And just by looking at the pixels, these neural networks were able to tell which digit was like 0, 1, so on and so forth. However, they might have struggled with more complicated data. For example, if you want to recognize natural images, say you want to classify different animals in the wild or something like that, and you're just showing pictures of these animals, neural networks struggled with this. However, one of the aspects that led to their success in them actually being able to successfully do this involved deep neural networks. So what you essentially did is you stacked layers one on top of the other, had connections going from one layer to the other, and you trained this entire architecture with gradient descent. And so this led to a lot of success in the neural network community, and this is something people refer to as deep neural networks. And one of the reasons it's thought that this is so successful is because it allows the neural network to build a hierarchical representation of the data. So here's some work on recognizing, for example, faces, cars, elephants, chairs. And you see that these different layers in the neural network are capturing different levels of information. And as the network goes deeper, it captures higher level information. For example, for the faces, the first level is just capturing edges. The second level is capturing higher level information like eyes, mouths, nose. And the last level is capturing faces. And this has led to a lot of success, not just for images, but for tasks like chemical reaction prediction, solving problems in high energy physics, and protein folding. Also led to successes in playing video games, beating humans at Go, solving the Rubik's Cube, which is what we're talking about now, and robotic manipulation. So the architecture, the deep neural network architecture we used is what is called a residual neural network. And so for the neural network, we have this input of 324, so that's 54 times 6, like we talked about. And then we have this, what's called a residual architecture that is adding these connections across layers, so these skip connections across layers. And essentially, we use the same architecture for all the puzzles we investigated, except the input here would be just changed based on the puzzle. For the 24 puzzle, we added 2 more residual blocks, but it wasn't really necessary. You didn't have to, but that's what we did. All right, so just like we saw with value iteration, the cost to go propagated outwards from the goal to all the other states. So when we're training our neural network, we're not going to be able to look at all the states. We're only going to be able to look at actually a small fraction of the states. And we're hoping that the neural network is going to generalize to states that it hasn't seen before. So we can't look at everything. We can only look at a small subset. And so what data are we going to use for this small subset? And so since this cost to go is propagating outwards from the goal, what we can do is the same thing. We can start from the goal and we can scramble it a few times, scramble it more, and scramble it more. And so this can ensure that this learning will propagate from the goal to the simpler states to harder and harder states. And so we can learn how to solve the Rubik's Cube by looking at a small fraction of the states, but ensuring that this learning can propagate from simpler states to harder states. And so we still use a modified version of value iteration, which is approximate value iteration. And so instead of keeping everything in a table, what we'll do is at every iteration, we compute this update, and then we use a neural network to try to learn this update. And then we do this in an iterative fashion, use that neural network to compute another update and learn that update with the neural network. And then that neural network is used to compute the next update, so on and so forth. And so we do this with, I believe there was 50 billion states. And so the neural network saw 10 on the order of 10 to the 9 states during training. And so this is, of course, a small fraction of 10 to the 19. And this was the same, for example, with the 48 puzzle. So this is an even smaller fraction of the state space because it has 10 to the 62 possible combinations. And so after learning, like I said, we could just behave greedily with respect to this cost to go function and select the action that's going to minimize our cost to go for every state. And we saw that by doing this, we weren't able to reliably solve the cube. So in this graph here, on the x-axis, you have the training iteration. On the y-axis, you have the percent of the cubes that were solved. And then each one of these lines represents the number of times you scramble the cube. And so up until about 7 times that you scramble the cube, it can reliably solve it. However, as you scramble it more and more, it becomes more and more unreliable. So we're going to have to add something onto this in order to be able to reliably solve the Rubik's Cube. So this takes me to search. And 1 second. So search would give AI agents the ability to think before they act. So they're able to think about, what would happen if I took this action without actually taking that action. So we can think ahead, and there are 2 different ways we can look at search. We can look at this as just blindly searching without any idea of how close we are to a solution, or searching in an informed manner. We have some estimate of how close we are. And so here again, in this tractor example, this tractor wants to get to this shovel here. We can apply some uninformed search where we're just blindly trying actions until we run into the goal state. And here's what this would look like. So here, all these red and gray squares are what the agent is thinking about before it acts. So you can see it found a solution, but you saw it was thinking in a very non-intuitive way. It was considering all these squares around it equally, even though the goal was to its right. And so this type of approach wouldn't work for the Rubik's Cube because we would eventually run out of memory. And so we need to do some type of informed search. And so if we use a simple heuristic to estimate how close we were to the goal, so what was our cost to go to the goal, then we could search in a much more efficient manner. And so that's what the search looks like when we have a heuristic that we're using to try to estimate how close we are to the goal. Well, it turns out this cost to go function that we learned with a deep neural network can be used as a heuristic for this informed search. And the search method that we use is a method called A-star search. And A-star search is a very popular search method, and it's frequently used to solve pathfinding problems. And the core idea is that different states are prioritized according to some cost. And this cost is computed by what was the cost it took me to get from the start state to this current state. And I'm going to add on to that, what is my estimated cost to go from this current state to the goal? And this estimated cost to go comes from our deep neural network that we learned through approximate value iteration. And so traditionally, A-star search is going to prioritize nodes according to this cost function and then look at nodes one at a time. But since we're using a deep neural network, we can take advantage of parallelism provided by GPUs. Deep neural networks often are expensive when it comes to computation. And so we can use GPUs and we can expand more than one node at a time. We can expand a bunch of nodes at a time. And we can use a method called weighted A-star search where we don't weight the path cost as much and put more emphasis on a heuristic function. And this can lead to the search being potentially faster and using less memory if we do this. All right, so how well did it work? So we could create test states for the Rubik's Cube and other puzzles by solving them, by scrambling them 1,000 to 10,000 times, and then just saying, these are our test states. And so we had 1,000 test states for the Rubik's Cube and 500 for all the other puzzles. And for some of the puzzles, it was possible to compute the cost of a shortest path by using these optimal solvers that take into account some domain-specific information about the puzzles. But it wasn't computationally possible for all the puzzles that we looked at. So we see here that for the Rubik's Cube, we were actually able to solve the puzzle optimally 60% of the time. And we were able to do this on the order of seconds. For the 15 puzzle, this was 99% of the time, and for the 24 puzzle, 96% of the time, and for lights out, 100% of the time. So if one is thinking about this in terms of, say, God's algorithm, then for the Rubik's Cube, 60% of the time, we were using the fewest number of moves possible. But one might say, what about the most complicated Rubik's Cube states? And this is going to be the ones that are furthest away. And so there are 3 states that are 26 moves away. And the more popular number for God's number is 20, but that's because they are counting moving a face 180 degrees as a single move. But here we use what's called the quarter turn metric. So that one is the half turn metric. This one is the quarter turn metric. So every move of a face counts for 1 move. So a 180 degree turn counts for 2 moves. And in that metric, God's number is 26. So there are 3 known states that are 26 moves away. And for the 15 puzzle, God's number is 80, and there are 17 states that are 80 moves away. And when we apply DeepCube to this problem, we actually saw that it's able to solve 100% optimally. And then for the 15 puzzle, it solves 17% optimally, but it's on average 2.28 moves away from a shortest path. All right. And then furthermore, we found that DeepCube was able to solve the puzzle in a way that if we investigated, we could find some type of properties about group theory there. So for example, conjugate patterns, where you take some move A, another move B, and reverse the move A that you took, are found in a lot of the solutions. And then the DeepCube algorithm oftentimes finds symmetric solutions to symmetric states. So if, for example, I mirror these 2 states, then I can solve the other by looking at the solution of the first one and just mirroring that solution. That would allow me to solve the other one. And so DeepCube often found symmetric solutions to symmetric states. And then so you can see this demo here. This should be up and running now, actually. And it was able, if you set the A-star search parameters correctly, it's able to solve the Rubik's Cube in just about a second or so. And so when this first came out, it got some attention by the media, and they were really excited that it could solve it in a second, but I wasn't actually paying attention to that. I was paying attention to the cost of the shortest path, but people were really excited that it could solve it so fast. So I actually wasn't really paying attention to this. But when it comes to other methods for solving the Rubik's Cube, like I mentioned, Thomas Rikiki's iterative deepening A-star search, and his ability to use group theory properties and those things about the Rubik's Cube, it can solve it even faster. It's just this approach actually didn't use any of this domain-specific information and only used artificial intelligence. Now, just because it can solve the Rubik's Cube doesn't mean that it can teach a human how to solve the Rubik's Cube. So this is what's called the black box in artificial intelligence. And deep neural networks are often blamed for that black box, but it's not just the fault of deep neural networks. When an agent is searching for a solution, it also does not share what it's thinking about and share it in a way that humans can understand. So we need to be able to try to peer into this black box to solve these problems. So, for example, the Rubik's Cube, we know that there's some knowledge that we could extract, but we actually had to know it beforehand before we extracted it. And then there's some interesting problems, say, in game playing. So this is DeepMind's AlphaGo, and it was able to beat the world's best Go players. And there are some moves it took that looked unorthodox, but actually ended up to having it win. But it wasn't able to explain why it took that move. All right, so we want to be able to create AI that can explain itself, and we are motivated by the way Rubik's Cube explanations are often done. So when you're looking online for different solutions to the Rubik's Cube, or you're teaching your friend how to solve the Rubik's Cube, we're often thinking about this in terms of sub-goals and algorithms we can use to achieve each sub-goal. So here is a beginner's method for solving the Rubik's Cube. You get the cross, first layer, second layer, cross on the bottom, and then solve all the corner pieces on the bottom. And so an algorithm would be something that, say, for example, is going to swap these pieces around. And we can use this algorithm if we want to swap these pieces around. And so furthermore, maybe you're not trying to solve the Rubik's Cube in this particular way. Maybe you have some ideas about how to solve the Rubik's Cube yourself, or you just want to explore different possibilities. For example, maybe you want to get all the corners first and then get all the edges in place or something like that. You should be able to collaborate with the artificial intelligence agent to be able to solve these in a way that you personally find interesting. Also, there are some unsolved problems that perhaps AI could help humans solve. For example, problems in theorem proving or chemical synthesis maybe can benefit from human guidance. And how can we then collaborate with AI to solve these problems together? So we have some very preliminary work on this, and we have a framework set up where a human is collaborating with this AI through a chatbot, also through a visual interface, and they can provide their own ideas, for example, about sub-goals they want to achieve or about algorithms they want to use. And they can also ask particular questions. For example, I'm in this position and I want to know how I can get the cross. And then we can use some black box methods, for example, this deep learning, this search, and combine this with methods that are explainable, for example, logic programming and knowledge graphs, to come up with solutions that are explainable to humans. And say, for example, you're telling them, well, in this scenario, you can apply this algorithm because this sticker here, this white sticker, is facing outwards, and the red sticker is facing the white face. You can actually apply D prime, F prime, RF to get this to get the cross from this position. And it's giving this example here. So in order to do this, we have to explicitly tell the AI agent concepts about the Rubik's Cube. So we have to tell it what a centerpiece is, what an edge piece is, what a corner piece is, what a layer is, all the stuff that we take for granted. We have to tell it that white is opposite to yellow. We have to tell it that a sticker can't be in more than one place at a time. All this information that we, think is obvious and we take for granted, a machine has to be explicitly told this. It doesn't know that, you can't take, one cubelet and put it in two places at one time. It doesn't know that. So we have to explain, the Rubik's Cube is this three-dimensional cube. It has its stickers, it has these cubelets, it has these properties, so that it can be able to explain to us how to solve the Rubik's Cube in a way that we can understand. And then I mentioned decision trees previously and how they're nice because they're interpretable. And so one way to think about telling people how to solve the cube would be to use a decision tree. So for example, here you might ask a series of questions before you use this algorithm. So do you have the first layer complete? Do you have the second layer complete? Are all the edges in the correct place? No. Is there a straight line? Yes. Are there three edges out of place? Yes. And maybe, if all these decisions are in place, then you can apply this algorithm. So that's a nice property about decision trees. However, this can get actually pretty complex pretty fast if you're not careful about how you code things. So say, for example, we just want to get one single kubelet in place. Um, and we have to ask a series of questions. So which side is the white sticker facing and which side is the orange sticker facing? And then that determines the actions that we take. Um, However, we would like to do this in a more interpretable, a more concise manner. So say for this very simple case, you can explain it in a much simpler fashion. So say, for example, you say, get at least one pair of stickers to match. And then if the white stickers are matching, then you can just turn the top face so that the orange stickers are matching too. And then if the orange stickers are matching, you can turn the orange face so that the white stickers are matching. And so this is a much more concise explanation, but this is going to involve going between this world of logic and knowledge representation to natural language and being actually able to generate this natural language. And then if people have their own ideas in natural language, actually processing that natural language to incorporate those ideas. And so we have a demonstration coming up at AAAI, and we have a interface that looks something like this, where we have a chatbot here, and we have a Rubik's Cube to actually give demonstrations about algorithms and how to achieve certain sub-goals. And so here are two of my students that are working on this project. And then also this work is done in collaboration with everybody here. And then here's some references. Okay, any questions?
I think we have a few questions in the chat box. So the last one coming from Amok, that he was talking about another way of representing the cube to the machine. So he asks that, can we use a vector to denote all the positions of the cube, like their lengths and directions from the center of the cube? Is that possible to feed it into the machine?
Yeah, that's possible. Yeah, for each cubelet, you have some just number that's saying how, yeah, just basically where it is on the cube. Yeah, that's possible.
Okay. Do we have any? Okay, Amok has another question. I guess he's typing it out. Amok, you can actually unmute yourself and ask the question yourself. Yash, can you help Amok with that? Yeah.
Yeah. Am I audible?
Yeah.
Yeah. So I wanted to know that if you can actually mathematically determine if there exists a solution to the Rubik's Cube, like any arbitrarily scrambled state, would there be a definite solution? Can we actually solve the Rubik's Cube? Something like that.
So there are certain positions that are impossible in the Rubik's Cube. So not as long as you start from, you use legal moves. So you start from the goal and use legal moves, you can solve any position. And this can just be done by just reversing whatever moves you use. But if you take one piece out and then just turn it, then just twist it, you won't be able to solve it using legal moves. And so there is a way to tell which ones are legal configurations, but I forget that. I forget how they do it.
Mm-hmm. Also, is it possible for the machine to know whether the corner piece is twisted from the initial configuration by looking at the arrays and stuff like that? Is it possible for them to know if a corner piece is twisted?
Yeah, so if the array shows, that these stickers are in this particular configuration, then you can recognize this.
If it's
okay. Say that it's illegal. Now, DeepCube is not concerned of the illegal move, so DeepCube itself can't know, but there are methods that can compute that.
Okay. Vivek has a question. Vivek, you can unmute yourself, maybe.
Hello.
Yeah.
So I wanted to ask if there are ways to quantify explainability? Suppose we get two explainable systems, and then will there be a way to evaluate them or something like that?
That's a great question. So there is some work of doing this quantitatively in planning literature. So looking at this, for example, the conciseness of the explanation, what information is captured in this explanation. Um, but the way that we're going to do this is mainly qualitatively. So actually having students interact with this system, getting their feedback on how good they think this system is, whether or not it's helping them solve the Rubik's Cube.
Okay, okay.
Okay. Do we have any more questions? If so, you can unmute yourself and ask. Yeah, also, Yash, you can maybe stop recording so that maybe some people maybe will show up, maybe because we are recording. Yeah. Yeah. Yeah.